In this video, we're going to go over the line of action of a force. In this case, the line of action is the location and direction that the resultant force will be acting on. And so, for example, we want to know how the uneven pressure distribution that's acting on our inclined plate, as we defined before, where that force is going to be acting on the plate, especially relative to the location of the centroid of that plate. Okay, so to find the line of action, we sum the moments about a point and assume the resultant force yields the same moment. Okay, so let's take a look at that. So we have the same example we have here, where we have a inclined plate at an angle alpha. We have the pressure increasing with depth. The pressure is defined as gamma psi sine alpha. So we have that same psi coordinate here, psi there. And then through our initial analysis, we found that that overall force is equal to the pressure of the centroid at psi c, which is shown here, times the area of the plate. Okay, and what we want to know now is where psi r is located. Where is that force effectively acting? And because the pressure is shifted down toward the bottom part of that plate, we know that that force will be below the centroid. So the resultant force will always be lower than the centroid in a fluid, for the pressure in a fluid. And this is shown in Munson 2.17. Okay? So we define psi r as the location of the resultant force, or the center of pressure. So again, it's kind of like a center of pressure, where the pressure is really going to act on this plate. Okay? So if we sum our moments, like we said before, we're going to sum the moments. We're going to get psi r f, the resultant force, is equal to the integral of psi df is equal to the integral of psi p dA. Okay? And we know that P, the pressure, is equal to gamma psi sine of alpha. So we can plug that into our equation and we get psi r f is equal to gamma sine alpha integral over the area of psi squared dA. And just like in our previous video on the hydrostatic pressure on a planar surface, we now, from our statics, have an expression for this term, and this is the second moment of the area. Okay? So that's the second moment of the area. And often it's convenient to express the second moment with respect to the centroid, i.e. as an axis that passes through the centroid. And to do that, we can use the parallel axis theorem to shift it. So we've given the second moment the term Ix, and we were going to express that relative to the centroid Ixc. And so we have Ix is equal to Ixc plus psi squared times the area. Okay? So that's how that works. And then what we want to do is substitute this expression back into our original summation of the moments. So we now have psi r f is equal to gamma sine alpha times Ixc plus psi c squared alpha. Okay, so now it's the centroid, psi c squared alpha. Okay, we know again that f is equal to gamma psi c sine alpha a from our previous lecture. So we can plug that into our equation. We get psi r times gamma psi c sine alpha a is equal to gamma sine alpha Ixc plus psi c squared area times area. Okay? And what this tells us is that the orientation and the specific weight don't matter. The line of action is simply a function of the area and the geometry. And you'll see that when I cross out the things that we see. So sine alphas in both sides, gammas in both sides. And so now we can rearrange this to get an expression that looks like this. Psi r minus psi c is equal to the second moment IXC over psi c times the area, where all of these terms on the right hand side, IXC, the second moment, psi c, and the area, are all dictated by the geometry. And this is given in Munson as equation 2.19 in your textbook. Okay, so in the next video we'll go over some examples of how to use the line of action and the hydrostatic forces to solve some engineering problems.